Two really important terms in the equilibrium theory of island biogeography are this term immigration and extinction. And again, these are, you have to think about these more in terms of local extinction and local immigration rather than, this is not a macroevolutionary term that we're talking about. This is a extinction in an ecological timetable, not in an evolutionary timetable. So extinction in this case means that it disappears from that island and it's not there anymore. Immigration means that it makes it to that island and establishes a colony there. Okay. So up until the 1960s, and this is where really start to see the island biogeography flourish in the 1960s, was a very static field. People thought that immigration and extinction would be one-time events. So think about a sweepstakes. If something makes it to an island, that's a one-time event, that colonization, and it either makes it or it doesn't. And we weren't viewing in the 1960s this idea that immigration and extinction could be static and would be ongoing through time. And so you had more growing evidence that this model was wrong, and that immigration and extinction should be thought of as continuing events. And we really didn't have the genetic data. We'll get to some island examples, some really cool ones where they've tried to reconstruct the pathway of immigration and extinction in different adaptive radiated groups like Hawaiian honeycreepers and Darwin's finches. Some very interesting patterns of colonization and extinction, and you see that it's very much not a static event. You have things constant, it's sort of like the evolution being a linear progression or a bush. Okay, linear progression would be this idea that immigration and extinction are static. They're not. You have lots of immigration and extinction events happening between those finches. It's not. We talked about this a little bit when we talked about in the previous chapter where we said, the pattern of colonization of Hawaii from the honeycreepers was from west to east. But it's not a direct linear progression from west to east. You have a lot of back and forth and a lot of extinctions and recolonizations. And we didn't have the molecular data in the 1960s to support this. So it was more theoretical, really. So we need to define some terms. This equilibrium theory of island biogeography came from Wilson and MacArthur. And these are the terms, the way that they defined them. Immigration would be the movement of potential founding population onto an island. Just because it makes it there does not mean that it becomes established, so the next term would be establishment. So if the founders survive and form a population, we would define that as establishment. So this term colonization includes both of the above terms. It includes immigration and establishment. Then that would be a successful colonization. And then this term extinction, again, it's local extinction. It's a loss of a previously existing population. So it's not a permanent extinction of that species. It's a loss of that species from a particular island.
So what would be the equilibrium theory?
will show you in the next slide. Looking at equilibrium. If you plot the rate of these two processes, immigration and extinction, against the number of species, they're going to tend to run opposite. Okay? So extinction, as you get more species, you're going to end up with a higher rate of extinction. Okay? Why would that be? As more species accumulate on the island.
Because the number of sources limited in the island.
That's right. So you have limited limited amounts of food, limited amounts of shelter. So you're going to have two biological interactions that are going to be working: competition and predation. Okay. As you accumulate more species, you're going to accumulate more competitors, and then eventually more predators. Okay. That's going to tend to limit the species. So species richness will extinction will increase as species richness increases. As species richness, likewise, immigration, as you get the number of species goes up, the rate of immigration will also go down. There are less available niches. As you accumulate species, you get fewer and fewer niches available in a particular island. So islands get more full. So the rate of immigration is naturally going to slow down as species richness goes up. Where the point at which these two lines cross is what we call the equilibrium number of species, or equilibrium species richness. So MacArthur and Wilson thought they could predict the equilibrium species richness for different islands. Now, what this does not account for are island size and island distance. Okay? This basic model. So we have to modify this model thusly. And you have this graph in Blackboard. So what you have are numerous equilibrium points for species richness. Every place these lines intersect is a different equilibrium point for species richness. And they have to do with how distant or close the island is, small, far, large, close, small, far. Okay, so let's look at these in more detail. So islands that are small and far away are going to have higher rates of extinction. All right? If you're small and far away, the idea of what we call a rescue effect is very small. So rescue effect is if you start to get a decline, we're out here in the middle of nowhere, and the population starts to crash because of a hurricane or something, a rescue effect would be new immigrants coming and recolonizing and re-establishing the species. So the probability of that is low, of a rescue effect, because you're small and because you're distant. And so the rate of extinction is going to go up with small, far islands. Likewise, large, close islands are going to have the lowest rate of extinction. Okay? Being big, so here we have a big island, moving really close to meeting. You have a higher probability of a rescue. The rescue effect is really high here. So if you get a big hurricane that wipes most of this population out, she can make more babies and send them over. Okay? So the rescue effect is going to be very, very more probable. Okay? So extinction rates lower, that's also going to make immigration rates higher. The large close islands, you're so close to the source. Okay? So the mainland is often seen as the source. We take our island, we move it back far away, we shrink it back down to a little bitty size of this marker. All of a sudden, immigration rates are going to become much less. It's going to be much harder to get immigrants from over there to this little marker. Okay? So you have this equilibrium balance between immigration and extinction, and then island size and island distance. Seems like a pretty good model. So rescue effect is going to be going to which islands are going to be more. The rescue effect is going to benefit which islands?
Closer.
Okay. Rescue effect is going to benefit closer and larger islands. What about close and small? Rescue effect going to be higher or lower?
Lower.
Lower. Okay. What about large and far away? Large islands far away. Those are the conditions sort of in between, right?
Large part is lower.
So it's also going to be lower, right? It's these these in betweens are going to be the ones that are like your large island that's far away or your small island that's close. Those are not represented real well in this model, actually.
Yeah, because I think the distance will be more important than how big is the island.
Okay, that's a great question. So which is more important?
The distance. You think more energy go there or more better optimal conditions with the island. I mean, Australia is big, but it's probably far away from here.
All right, so you say what now?
As an example, is
You said distance is more important.
yeah.
And why?
Well, because it takes more energy and better optimal conditions to reach that island. A long trip, many things could happen.
High risk. Anybody would argue the other side? The size would be more important?
Well, the rescue effect it could be.
Okay, so size. Now we can start to think about exceptions. So, island size versus distance. Well, tell me what species you're thinking about.
I'm not thinking of any particular species.
Okay, so let's ask this a different way. Were you thinking of a particular species, or were you thinking generalities?
Generalities.
Okay, let's think of a lizard versus a bird.
Well, distance would be more determined by a lizard.
Okay.
Yeah.
So in this case, distance is probably more important from a lizard standpoint. What about a bird? Distance doesn't matter as much.
It depends the bird, I don't know.
It depends the bird. That's
Yeah.
true.
Because, I mean...
Did you say just amphibians? Because amphibians
Some birds are good flyers, parrots are not. Okay, we're talking about large birds like a parrot, and distance probably makes a big difference. If you're talking about a bird that can fly and that flight length is not a limitation, then island size might be more important. So it's hard to generalize about some of these issues. So this is starting to point out some of the weaknesses of this particular model. Models in biology are great. You guys took, how many of you had genetics? Most of you are in genetics. What's one of the basic models of genetics that you use as a null model to look to see whether natural selection has occurred? Hardy-Weinberg?
Oh, yeah.
You guys remember Hardy-Weinberg model?
Yeah.
Because the Hardy-Weinberg model is a neutral model. It's a null model. And if you violate any of the assumptions of Hardy-Weinberg, then you have natural selection or genetic drift or something like that happening in the population. So you rarely find Hardy-Weinberg in the wild, in nature. Okay? It's really great as a model that you can throw darts at and find things that, because you always find exceptions to Hardy-Weinberg. That begs the question of why do you find exceptions to Hardy-Weinberg? That's you kind of have to view this MacArthur and Wilson island biogeography model in a similar way. So one of the first weaknesses we're starting to get into right here is that it ignores species identities. This has been called MacArthur's paradox. It's just looking at species richness. It's not looking at birds versus lizards. It's not looking within birds as to what their flight abilities are. So species identities actually matter when we start to get to the nitty-gritty of the details of this model. And then it's the intermediary cases. So immigration and extinction can be interdependent, as we've kind of alluded to here. Okay, so when we're talking about the rescue effect, if an island is close to the mainland, regardless of size, extinction may be low because immigration is very high if it's close to the mainland. So immigration, if you look at the model, immigration and extinction are mutually exclusive. And it's where they intersect where you determine species richness. I'm arguing here that they're not necessarily completely independent of one another. If an island is close, I'm not going to drag the table over here again. If an island is close to the mainland source, it's going to benefit both on the extinction side and the immigration side. Extinction will automatically become lower, immigration will automatically become higher.
Oh, because we go back and forth.
Because they can go back and forth very rapidly. This is a term we haven't used in target effect is specifically to larger islands.
So would you say benefits larger islands or more
Um,
prevalent?
It doesn't matter how far away from the mainland it is necessarily. Larger islands are always going to get more immigrants. They just are. And it goes back to Schoner's rule. If area is bigger, you're going to get more species richness. So bigger islands are always going to have more species richness because they're a bigger target, regardless of the effect of extinction. If we make this entire whiteboard an island, and we make this an island, and we all stand up at the front of the room, and we throw markers at the back of the room, it's easy to hit that. I was aiming for that whiteboard. It's easy to hit. I just demonstrated the target effect. I missed. I could probably throw it 10 more times.
You broke the marker.
Dang. See, that's what
Did you
happens.
just buy that one?
No, see,
Extinction.
species, when they try to hit that small target, they can get broken.
Extinction.
Extinction. The species just broke, trying to make it to that island. Okay? So small targets are hard to get to.